In our last lecture, we looked at what we called the partial derivative permuter, and it allowed us to do some interesting things. There are other tricks that we can play with partial derivatives, and one of them is what I will call the partial derivative inverter. And you see it at the top of the slide here. It says that the partial of y with respect to x is equal to 1 over the partial of x with respect to y. So it's kind of like an algebraic relationship, but it's a very powerful trick that you can employ when you look at partial derivatives. So again, let's just consider the ideal gas formula, PV equals nRT. And let's use P as x and V as y. So dP, first of all, P is equal to nRT over V. So dP dV would be equal to minus nRT over V squared. So let's see if that is equal to 1 over dV dP. So V is equal to nRT over P, and dV dP is minus nRT over P squared. So dP dV should be equal to 1 over dV dP. So if I plug those two in as I do in the next to the last line, and then what I do, of course, is I do a little bit of manipulation. I flip the P squared onto the top of the right-hand side. So I have P squared over nRT. And then for P squared, I substitute nRT over V and square it. I cancel the nRT terms, and I get that that is equal to minus nRT over V squared. So we can show that this is true in that particular case. Maybe what you would like to do is maybe take another simple equation like D equals M over V and see if you can find the partial of D with respect to M and see if that is equal to 1 over the partial of M with respect to D, and it should be because this holds in all cases. Kelvin went about defining what is temperature. Now, really, if you start to think about it, temperature is a rather abstract measurement. Essentially, what you're doing when you measure temperature is you're measuring energy content. So in some way, it is gauged as the energy content that a material has based on the ambient conditions that it's subjected to. So there's some connection between Boltzmann's constant temperature and internal energy, of course, and we measure temperature with thermometers, of course, by expanding liquids or changes in resistance of a conductor. We use that as some guide to what temperature a system possesses. And of course, Kelvin had earlier done a discussion about absolute zero and the point at which all internal motion of matter ceases. Here he's just giving a general definition of temperature, and he begins with the fundamental equation that we have described in our last lecture. Remember, by combining the first and second laws, we said that du is equal to TdS minus PdV. So what Thomson then did was just state that u is a natural function of the variables s and v. So it has to be equal to then the partial of u with respect to s at fixed v, ds, plus the partial of u with respect to v at fixed s, dv. Now we talked at great length in our last lecture about how to write that mathematical statement for any exact differential. So if you're not clear about how I can state that u being a function of s and v can be written in this form, please refer back to the previous lecture where we discussed that at great length. Now, by comparing the top and bottom equation, I see directly that a definition of temperature can be found from du ds at fixed v. Now, it turns out that for reasons that I'm not 100% clear on, but Thomson actually defined the inverse of temperature, 1 over T. And so he just simply took that expression and applied the inverter to that expression and said that that should be ds du at fixed v for 1 1 over T. And so he's essentially saying that the entropy or temperature is defined as how entropy changes with internal energy at constant volume. Now, remember, for at constant volume, any PDV, any work term is gone from the internal energy, and at constant volume, du is equal to c sub v dt, or the internal energy is simply a function of temperature. So if we look at how the randomization of a system changes as the internal energy of the system changes, that should be proportional to 1 over the temperature of that particular system. Look at another handy relationship that is true of partial derivatives, and that is what I will call the interchanger. Notice on the left I'm taking the partial of z with respect to 2 variables. So I'm taking the second derivative of z, but I'm taking the second derivative of z with respect to 2 independent variables. So z is a dependent variable, it's a function of x and y, but instead of taking d squared z dx squared or d squared z dy squared, I'm taking d squared z dx dy. And what I'm going to claim is that the order in which I operate on z with the partial with respect to x or the partial with respect to y is independent. This is because they are independent variables. Now, against those of us who have, and I'm pretty sure everybody in the class has done this, has taken quantum mechanics, a derivative is an operator, and a second derivative is an application of essentially 2 operators. Back-to-back derivatives is applying an operator twice. Now this is being applied so that they are 2 separate operators, ddz or dz on dx or dz with dy. So I can either take ddx on z and then take ddy on the result, or I can take ddy on z and take ddx on the result, because they are independent variables. This wouldn't work if they had some relationship with regard to each other, which oftentimes the variable z, for instance, when you have conjugate variables in quantum mechanics, this becomes an issue because the action of taking one derivative with respect to the function collapses the function and removes some of the possible states, and so you have weirdnesses based on the order in which you happen to take the derivatives in cases like that. Here we're going to not consider conjugate variables, we're going to consider independent variables that are simultaneously observable, if you like. So I can take the partial derivative in either order. So let's again take our ideal gas formula and notice that if we solve that for P, which is nRT over V, and now I take the derivative of P with respect to V or T or V, it doesn't matter which order I do those derivatives in because I get the same function. Now this might seem trivial, but later on we'll see the utility of this idea of interchanging our partial derivatives. Several slides show the utility of this idea of interchanging partial derivatives. And this idea was introduced into thermodynamics by James Clerk Maxwell. Now, of course, the name James Clerk Maxwell should be familiar, even though we're chemistry majors here in this class. But James Clerk Maxwell is, without question, one of the absolute most important physicists of all time. He was a Scottish dude, as you can see, who lived not a very long life at all, but he lived a very fruitful life in terms of his scientific contributions in the mid-19th century. Of course, most celebrated was his contributions to electromagnetism, incredibly elegant work on the connection between electricity and magnetism, which was not theoretically understood before he did his incredible, and I can't overemphasize to you the incredible insight that he provided to electricity and magnetism. But that wasn't the end of his contributions to science. He along with Boltzmann, looked at the kinetic theory of gases and kind of pioneered the idea of the ideal gas by looking at how the velocity or speed of gas particles could be modeled with distribution theory. And it pioneered the kinetic theory of gases, really cool stuff there too. But also here in this aspect of thermodynamics, he looked at how you could apply these actions of interchanging partial derivatives to the fundamental equation of thermodynamics. Now remember, what that fundamental equation of thermodynamics is a combination of the first and second law. du is equal to, of course, PDV, TdS minus PDV, and that is derived by putting together the concepts of behavior in the first law and the second law simultaneously. Again, to see where this ultimately comes from, it's really not a huge, tricky thing to do. If we consider the first term to be dq and then substitute what dq should be in terms of entropy, put that in there, you get this simple relationship that is incredibly powerful, and we're going to be exploring it pretty much the whole of our material for this particular unit. Okay, now, since u is an exact differential, it's a state function, we can write it as we talked about again last time by looking at s and v as the independent variables and u as the dependent variable. Again, explaining what this expression, second mathematical expression, is saying. I look at how u varies in the s plane while I hold v fixed, so I'm in the us plane on a three-dimensional surface, v being held fixed. I'm looking at the slope in the us plane, that's the change in u with respect to s. Then I multiply by the increment of change s in that plane, and I get some change in u. Then I go to the other independent variable, where now I will keep the s fixed and look in the uv plane. And in the uv plane, I'm looking at the slope of the u with respect to v in that plane, and then I'm going to multiply by the increment of change v. If I sum those two increments of change up, I'll get the total increment of change in u. Because it's an exact differential, I can do these things independent of each other. Now, by direct comparison of the top equation to the second equation, I note that the partial of u with respect to s at fixed v is equal to t, and I note that the partial of u with respect to v at fixed s is equal to minus p. So now let's apply the interesting aspect of the interchanger to these partial derivatives. If I now take the partial with respect to v of du ds at fixed v, that has to be equal to the partial with respect to s of the u dv at fixed s. So what that's saying is that since the u ds at fixed v is equal to t, then the partial of t with respect to v at fixed s has to equal, and then on the right-hand side, if I substitute the third equation down into the fourth equation, I see that I can put p in for that second partial derivative, and so the partial t with respect to v at fixed s has to be equal to the partial of p with respect to s at fixed v with a negative sign in front of it. Now, the immediate utility of an expression like this might not seem that interesting or useful, but as we will see going forward, we can get all kinds of interesting tricks that we can apply onto different thermodynamic processes by manipulating the things that you see in these particular equations. So this is the first of our so-called Maxwell relations. This Maxwell relation is derived from the fundamental definition of the internal energy. What we're going to see on subsequent slides is take the fundamental equation for enthalpy and find its Maxwell relationship. Then we're going to take the fundamental equation for the Helmholtz energy, find its Maxwell relationship. Then we're going to take the fundamental equation for the Gibbs free energy and find its Maxwell relationship in a very similar fashion to what we have done here. This slide shows a derivation of our second Maxwell relationship. This time we will begin with enthalpy, and by combining the first and second laws, remember H is equal to U plus PV, DH is equal to DU plus PDV plus VdP. Then if we substitute the fundamental equation for DU into the beginning of that, we end up with DH is equal to TdS plus VdP. So in terms of the fundamental equation of thermodynamics, H is a natural variable that is a function of entropy and pressure. So H as a function of S and P has the definition you see above. So of course H is an exact differential, as we've talked about many times over. And since H is a function of S and P, it can be expressed as we have done in the second equation. You should be able to write an equation like that anytime I give you a function and the variables, if it's an exact differential, the variables that it's a function of, you should be able to write an expression as you see in that second equation. Now what we can do is compare the first equation to the second, and we note that temperature is defined as how enthalpy changes with entropy at constant pressure, and we see that volume is defined as how enthalpy changes with pressure at constant entropy. So these are directly relating the fundamental equation to the behavior of an exact differential. Now at first glance, again, these might seem crazy and completely useless relationships, but you can think of how you could do an experiment like this in laboratory. Like for instance, if I measure how enthalpy varies with pressure and I do it in an adiabatic experiment where what does that mean? I just insulate. I insulate to the surroundings, my experimental setup. I don't let heat out of the experiment. I don't let heat into the experiment. So I have an insulated container. Now somehow I can measure how does the enthalpy change with pressure. Well, that when I look at that closely, the slope of the function will be equal to the volume that the system is occupying. When I look closely at how that variation of those mechanical pressure is to the thermodynamic enthalpy. Okay, now with the third line, what I'm going to do is apply the partial derivative exchanger. The first, I see that dH ds is equal to T, but since H is always also a function of P, let me take ddP on dH ds. And that's saying, let me take ddP on T. And that has to be equal to taking ddt on P. So, or on V, excuse me, on V. So, I said that wrong. Let me scratch and reverse that. Since H is also a function of S and P, I can take the partial of H with respect to P and then hit it with the derivative with respect to entropy on the outside of that. So according to the interchange of the order of taking partial derivatives, ddP on dH ds has to equal dds on dH dP. And then I can just substitute what I know for dH dP and dH ds from the third equation down. And that tells me that the temperature changes with pressure adiabatically has to equal how volume changes with entropy isobarically. So this is the second of our Maxwell relations. Now let's look at what Maxwell had to say about the new function that we introduced in our last lecture, and that was the so-called Helmholtz function. It's often called the work function. A actually stands for Arbeit, which is German for work. And by combining the first and second law, as a matter of fact, first of all, the definition of A is that it's equal to U minus TS. And if you then take the derivative of that, dA is equal to du minus TdS minus SdT. Then if you substitute that du is equal to TdS minus PdV, you come to the conclusion by combining the first and second law that an increment of change of the Helmholtz function is equal to minus PdV minus SdT. Again, you can refer to the first lecture in this series for more insight into the origin of that equation. So A, this new thermodynamic function, is a natural variable of the independent variables V and T. Now these are getting a little more useful to us. The independent variables are mechanical measurements of the volume and temperature of the situation. So since A is a function of V and T, I can write it being an exact differential, as you see in the second statement. Again, this should be something that I hope is becoming second nature to you. If A is a function of V and T, I can express it as the slope of A in the AV plane times the increment of change V plus the slope of A in the AT plane times the increment of change dt. So that'll give me the total change in the variable A, since it's a function of these two variables alone. All right, so then by comparing the first and second equations, dA dV at fixed t is equal to minus p, and dA dt at fixed v is equal to negative s. So then Maxwell hit this with the partial derivative interchanger, which says that since A is a function of t and v, it doesn't matter which order I take partial derivatives of A with respect to t or v. And since then I can note from above and make the substitution of the variables from the third into the fourth, that dp dt at fixed v is equal to ds dv at fixed t. Now this is starting to become interesting, in my mind at least. If I'm interested in how does the entropy of a system change isothermally as I change its volume, what this is saying is I don't have to measure or try to design some weird experiment where I measure how the entropy changes with volume. What I can do is do a fixed volume experiment and measure how the pressure changes with temperature, and I'll get the information I want from that experiment. That's kind of out there, that's abstract. When people went and looked and designed experiments to test this, they found, hey, this works. So this is just abstract mathematical application. And then again, as I talked about before, this led people to experimentally explore, are these statements true? And it turned out, yeah, they were true. There's one more Maxwell relationship to explore. That is the Maxwell relationship that is derived from the Gibbs function. Gibbs is a function that we introduced last time. It's more commonly referred to in biology or chemistry as the so-called free energy. And really what you could think of it, and I talk about this at some length in the first lecture, that is that the reason this is called the free energy is this is what else is available energetically after expansion work has been dealt with. So if there's any electrical energy available from some electrochemical process, this would be how that electrochemical energy in particular, that's probably the most commonly found form of energy in chemistry other than the work of expansion and contraction or the energy of heat. This would be that form of energy and form of how and when electrons transferred. So that's very commonly related to this particular free energy expression. And G is defined as H minus TS. So dG is dH minus TdS minus SdT. And if you stick in the definition of dH, which we see on the previous slide was TdS plus VdP, when we stick that in here, we get the dG from the combination of the first and second law is VdP minus SdT. And so G is a natural function of P and T. Again, this is another reason for the great utility of the Gibbs energy in thermodynamics. It's a natural function of two mechanical variables that we can set up in the laboratory, the pressure and temperature of the environment. So, since G is a natural function of P and T, I can write it, and since G is an exact differential, I can write it in the form of an exact differential that we have now seen many times over in our time together this semester. Now, by comparing the first and second expressions again, I see that the volume of a system is equal to how its internal energy changes with pressure at an isothermal case, and that the negative of the entropy of a system is how the Gibbs function changes with temperature in an isobaric case. So then what Maxwell did to those relationships was he inverted the order of the independent variables in terms of taking the partial derivative of G with respect to them. So I can take dG and hit it with dP and then dV, or I can take dG and hit it with dV and then, or dt and then dP. So I can take those two partial derivatives in either order. Then by substituting what I see in the third line into the fourth line, I come to the conclusion that dV dt at fixed P has to be equal to minus ds dP at fixed T. Or, if I'm interested in an isothermal experiment in which I'm varying the entropy with pressure, I could measure that abstractly by looking at how the volume varies with temperature at fixed pressure, which is pretty easy to do in a laboratory. I can heat or cool something off and see how much change in volume it experiences, and that gives me information about its entropy change. Again, when Maxwell presented these ideas, experimentalists immediately dove on it to see if, hey, these things are true. And this, again, is one of the incredibly important applications of abstract mathematical thought to the design of experiment, which is incredibly important in modern science. Again, I argued many times with you about the phenomenological nature of science before this. People observed what they saw and made a formula. Essentially here what we were doing is we're making a formula from abstract mathematical application and then looking for the observation that that formula can be verified. Completely different paradigm in how science is done, and a very important step forward in human abstract thought. It's just kind of really deep stuff we're talking about here. Now look at several applications of the power of these Maxwell relationships that we have now come to the conclusion that can be derived from abstract mathematics. Let's begin with a discussion of the internal pressure. We have talked about the internal pressure several times during this semester. If we, instead of thinking of U as a function of S and V, we think of U as a function of T and V, then du is equal to du dV at fixed T plus du dt at fixed V. Or du is c sub V dt plus pi t dV. So that is one way in which we originally thought about the internal energy. And then what we did many times during the course of this semester is we stated that pi t is 0 for an ideal gas. An ideal gas has no internal pressure. Now, what internal pressure is kind of trying to do is measure the intermolecular force that these particles that make up the gas are experiencing on one another. Let's think about what this is saying. The internal energy changes with volume. How does the internal energy change with volume of the gas? Well, I'm going to put the gas particles further apart or closer together. And what that will do is change the intermolecular force they are exerting on one another. The push or pull they feel due to the separation in space they are experiencing. What I'm claiming is, for an ideal gas, since the only mechanism of energy it can contain is kinetic, there's no potential of attraction between the gas particles, so it doesn't matter how far apart they were, particularly if that is isothermal. Kinetic energy of an ideal gas increases or decreases as temperature increases or decreases. It does not increase or decrease as I put the molecules closer together or if I space the molecules further apart. So pi t, at least in a hand-waving sense, we have argued many times over, it must be 0 for an ideal gas. Now what I'm saying here we should be able to do is we should be able to prove that based on the conclusion of Maxwell. Here's how I'm going to do that. I'm going to derive an alternative expression for du dv at fixed t. And I'm going to do that by taking the fundamental equation for internal energy. du is TdS minus PdV. Now what I'm going to do is manipulate it to make it look like pi t. And to make it look like pi t, I need to take the derivative of u with respect to v and set that at fixed temperature. So that's what I do on the third line. I just literally divide both sides of the second line by v. Then I impose constant t, which makes it, instead of a du dt, a partial u, a partial v. So again, all I did going from the second to the third line is divide both sides by dv. Then I imposed constant t, which changes it from dv into partial v. So that says that the u dv at fixed t has to equal to t ds dv at fixed t minus p, because of course dv over dv is 1. So that term cancels in the second part of the right-hand side. Now, that might not seem very utile, but if I go to the fourth of my partial, I'm sorry, it's not the fourth, it's the third of my Maxwell equations, the one that was derived from the Helmholtz function. From the Helmholtz function, I learned that dp dt at fixed v has to be equal to ds dv at fixed t. So in the third line down, I'm going to substitute the fourth line into there, and what I learn is that the internal energy, the internal pressure, pi t, is equal to du dv at fixed t, and that is equal to t dp dt at fixed v minus p. Now another thing you should note is that this has units of pressure. Now that can be seen from taking du dv at fixed t, and at fixed t, du is equal to p dv, and so if I take the derivative of that, I'm getting du dv at fixed t has units of pressure. And of course you can hopefully get from the right-hand side that has units of pressure as well. So now we have a general expression for pi t. This was derived not indicating I was using an ideal gas or a real gas. So the bottom expression that you see, pi t is t times dp dt at fixed v minus p. That is a general expression, true whether you have a real gas or whether you have an ideal gas. In this slide, I'm reviewing concepts which we have introduced. It's been a while now, about if we consider the internal energy to be a function of temperature and volume, then being an exact differential, I can write it in the form you see in the top equation. And then from the definitions that we introduced earlier, that the constant volume heat capacity is how the internal energy changes with temperature at fixed volume. And this variable that we talked about on the previous slide, the internal pressure, is how the internal energy varies with volume at fixed temperature. I can then represent du is equal to c sub v dt plus pi t dv. Again, this is an exact statement true for any gas, whether it is behaving real or whether it is behaving ideal. Now, what we have argued, and I just argued on the last slide pretty extensively, I argued that if the gas is ideal, pi t is 0. That's because there's no change in internal energy as you move the volumes closer together or further apart, as long as the temperature is being held fixed. The only way you can change the internal energy is to change the temperature. So pi t is 0 ideally. Now that we have this new expression that we found from Maxwell's relationships in the fundamental equation of internal energy, let's see if we can prove that statement that we made with the hand-waving arguments previously. So 2 slides back, what we found was pi t has to be equal to t dp dt at fixed v minus p. Again, a true statement for any system, whether it's real or ideal. But now let's put PV equals nRT into this, and P is equal to nRT over V. So dP dt at fixed V is nR over V. So if I stick that into the first of my partials at the top, pi t is equal to T times nR over V minus P. And of course, T times nR over V, if I substitute for P equals nRT over V, I get that pi t equals nRT over V minus nRT over V for any gas at any volume, any temperature, any amount I want. Pi t is 0 if the gas is ideal. So now, not only can we hand-wavingly argue that the internal pressure of an ideal gas is 0 with the ideas of Maxwell relations and the fundamental equation, we can mathematically prove that the internal pressure, of an ideal gas is 0. Let's look at what the van der Waals equation says about its internal pressure. So again, same definition. Pi t is either du dv at fixed t, but now using the combination first and second law and the Maxwell relation, it is also shown on the top of the right, and the van der Waals equation. And now remember, this is the so-called reduced or molar volume van der Waals equation. I literally divide by n through the equation. So P is equal to RT Vm minus B over or minus A over Vm squared. So dP dt at fixed V, which I need to put in my pi t expression. Notice the second term has no temperature dependence. The first term, taking its derivative with respect to P, gives me R divided by V minus MB. So when I multiply that by T and subtract it from P and substitute for P the van der Waals equation, I get that the RT over Vm minus B terms cancel, and that pi t is equal to A over Vm squared. So what we're saying is the internal pressure, and this is one of the beauties of the van der Waals expression, the second term of the van der Waals equation is the so-called internal pressure that this gas is exhibiting. Remember when we discussed the van der Waals equation oh so long ago now, the second term, that A parameter, is describing the mistake that the ideal gas formula exhibits due to the actual attractions that the molecules have for one another. So it should not be surprising then that the internal pressure of the van der Waals gas is a function of the term that contains this magic parameter A. It is the term that corrects the ideal gas formula for the stickiness that gas molecules actually display due to the dispersion forces that they possess when they're flying by each other, and that sticks them together a little bit, and that lowers the pressure they would exert on a container wall, since they're not going to ram into the walls with the maximum speed they would have if they are not sticking to one another. Let's use our newfound power to manipulate thermodynamic expressions using the inverters and partial derivative exchangers and Maxwell relations. Let's look at those applications to a cousin of the internal pressure. And that cousin of the internal pressure is the so-called isothermal Joule-Thomson coefficient. Define mu sub T is equal to dH dP at fixed T. How the enthalpy changes with pressure isothermally. This is again called the isothermal Joule-Thomson coefficient. This should be compared to what we just looked at on the previous slide, which we called pi T. Pi T was du dV at fixed T because U was a natural function of temperature and volume. H, on the other hand, is a natural function of temperature and pressure. So this is very akin to that internal pressure expression. Now all I've done is replace the U in that expression with H, and I've expressed or changed the variable V from the internal pressure into P. So UT is a close relative to pi T, believe it or not. And so guess what? I think it'll have the same kind of relationship for an ideal gas that we saw pi T has for an ideal gas. But let's save that for an upcoming slide here. What I'm going to do is and this is something that you should get comfortable with being able to do. I'm going to see if I can derive an expression for mu T based on the fundamental equation of enthalpy. Remember, the fundamental equation of enthalpy is derived from its first and second laws of thermodynamics, and the beginning point would be that dH is equal to TdS plus VdP. Now the game is this: make that second expression look like the top expression. How do I do that? Well, I need mu T to be the derivative of H with respect to P while I'm holding the temperature fixed. So I'm literally going to do that to the second equation. I'm going to take that expression, take its derivative with respect to P, and then impose that this is a partial derivative by holding the temperature fixed. So the third equation is taking the derivative of the second equation by P, dP, then stating that I want to make it a partial derivative by holding temperature fixed. So I divide the left-hand side by dP and hold T fixed. So I'm going to divide the right-hand side by dP and hold T fixed. So you'll notice I do that, and of course dP over dP is 1. So dH dP at fixed T must be equal to T times the SPT at fixed SPT fixed T plus V. Now that might not seem particularly practical until I turn to the fourth of my Maxwell relations, the one derived from the Gibbs energy. And that says that the SdP at fixed t is equal to dV dt at fixed p. So I substitute the fourth of my Maxwell relations into the third expression, and I find that the isothermal Joule-Thomson coefficient is V minus T dV dt at fixed p. Again, this is very similar to the internal pressure in its appearance. You can compare the two expressions on this one to the one on the previous slide to note its similarities. Continuing this theme of the similarity, or the relationship, if you like, between the internal pressure and this isothermal Joule-Thomson coefficient, let's consider H to be a function of T and P naturally. So then, being an exact differential, I can write the top expression for dH based on it being a function of variables T and P. The first term is simply the definition of the constant pressure heat capacity. So for that first partial, I can make that substitution. Now notice the second term is how I defined on the previous slide this isothermal Joule-Thomson coefficient. So what I can come to the conclusion of is that dH, the increment of change of the enthalpy, has to be equal to C sub P dt plus mu T dP. Now again, this is an exact expression. It is not simplified in any way, shape, or form. This holds for any gaseous substance, whether it's real or whether it's ideal. It actually holds for any liquid or solid substance as well. Now again, what I'm claiming is that this is a very similar expression to what we saw for the strict definition of the internal energy. That was du equals C sub V dt plus pi T d, C sub V dt plus pi T dV. Here, since H is a function of T and P, dH is C sub P dt and mu T dP. Now again, we could make arguments about this second term when we have a constant temperature environment. When we have a constant pressure environment. This second term should vanish in the ideal case, because for the ideal gas, dH is equal to C sub P dt, whether the pressure is constant or not. That's what dH is equal to. So that second term must be zero, generally speaking, for any gas that's behaving ideally. So let's see if we can come to the conclusion that that is true on the next slide. Okay, so we have our isothermal Joule-Thomson coefficient defined as dH dP at fixed T, and by combining the first and second law with Maxwell's fourth relationship, we see it can be measured from mechanical variables, volume and temperature. So this is how it can be measured from the volume and temperature. So ideally, of course, since PV is equal to nRT and V is equal to nRT over P, dV dt at fixed P is nR over P. So I can substitute that into the second term, then substitute for the volume that is nRT over P, and guess what? This isothermal Joule-Thomson coefficient is zero if the gas is behaving ideally. Now you should check for yourself what you think it might be if the gas is behaving as a van der Waals gas. See if we can find expressions for the heat that must be added during an isothermal expansion. Now remember, if I have a gas and it's expanding isothermally, expansion means you have to expend energy. You have to push the external atmosphere back, or it has to push against the piston to push outward. As it is doing this pushing, it should be expending energy upon expansion. If it's expending energy upon expansion, it should be cooling off as it does so. So in order to remain an isothermal process, the gas must absorb heat energy from the exterior as it undergoes this isothermal expansion process. Let's see if we can show how that must come about by beginning with the fundamental equation, actually not the fundamental equation, the equation for the internal energy that is true for any gas, real or ideal. That is that du is c sub v dt plus pi t dv. Now because the process is isothermal, dt is 0, so du is just pi t dv. And du, of course, is dq plus dw. So I can solve that for the heat that must be exchanged. That has to be equal to pi t dv minus dw. And since dw is pdv, or minus pdv, excuse me, dq is pi t dv plus pdv. Now ideally, pi t is 0, so q is the integral of pdv, and since I'm going to do this in a reversible process, for p I substitute nRT over v. I factor out the terms that are independent of v, which are the n, r, and t, and so I integrate that expression. The heat that is input into the system, since it is expanding, if Vf is bigger than Vi, that's a positive heat being put in, and it's equal to nRT ln Vf over Vi. Now what if the gas, instead of being ideal is a van der Waals gas? Then pi t for the van der Waals gas, as we saw in the previous expression, is n squared a over v squared. So I have to integrate that part of the expression, and I have my plus my nRT over v minus b minus n squared a over v squared, which I have to integrate as well. So notice the n squared a over v squared integral terms cancel. I have one at the front and one at the back. So really all I have to do is take the integral of nRT divided by v minus b times dv. Again, remember, look from the above expression, two of these integrals are canceling. And when I integrate that expression, I get something very similar that I got for the ideal gas, but in the van der Waals case, instead of just being nRT ln Vf over Vi, it's nRT ln Vf minus b over Vi minus b. So the only difference is a subtle difference for the heat that must be added upon reversible expansion of a gas, whether it's ideal or whether it's van der Waals. Let's define some other mechanical variables that we can measure for substances, including things like the expansion coefficient. The expansion coefficient, as you see here, is defined as 1 over v dv dt. Now, if you think about the units of what this would be like, the v has units of volume, the t has units of temperature, of course, so I have volume over volume divided by temperature units. So the units of expansion coefficients are inverse temperature. So we should keep that in mind when we go to measure these things later on. That's what the units of these should be like. Now, this is the general coefficient of expansion definition. If you have solids, typically like a metal rod or something like that, we often call this the coefficient of linear expansion. And why do we call it that? Because typically what happens, if you have a lengthy rod with a small cross-sectional diameter, it expands more than it expands linearly more than the radius of the area, this cross-sectional area changes. So the rod will get longer without getting noticeably thicker, is what we're saying. So very often this is the coefficient of linear expansion. That's usually given in alpha L, which is essentially the V is replaced by L. It's 1 over L dL dt. This is commonly employed for how materials expand and contract when they're in the solid form. So let's just look at the general alpha, 1 over V dV dt, if the gas is ideal. A V equals nRT over P. So dV dt, of course, then would be nR over P. So I take 1 over V times nR over P, and I substitute for 1 over V, that is P over nRT. And so when I simplify that down, we see the expansion coefficient of an ideal gas is 1 over its temperature, its Kelvin temperature. So what is that saying? If you have a gas at very high temperature, it's not going to expand very much as temperature changes because it's already occupying a big volume. 1 over T is a little number. If you have a gas at a low temperature, then 1 over T is a relatively big number. So gases expand much more dramatically when you put a little bit of energy into them and the temperature raises slightly at low temperatures than compared to when you put a little bit of energy into them and they're already at a large volume. The volume change is not nearly as dramatic at a high temperature. The expansion of the gas is not nearly as dramatic at a high temperature as it was at a low temperature. Let's look at another thermodynamic observable that is commonly measured for materials, and it's called the isothermal compressibility. How squeezable the gas is, how its volume changes with pressure at the conditions that the temperature are held fixed. It is defined as 1 over V dV dP at fixed T. Now again, just by dimensionally analyzing that top expression, I'm going to divide whatever volume units I have out of this expression, and I'm going to be, those are canceling. I'm going to have 1 over pressure units that these isothermal compressibilities are going to be measured in. So again, that's going to be say something about how much pressure you're applying, how big this property is going to become. Okay, so why is there a negative sign? That gives these values a positive value because remember, V and P are inversely proportional. When volume goes up, pressure goes down. When pressure goes down, vice versa. When volume goes up, pressure goes down. When volume goes down, pressure goes up. So the sign of dV is always opposite the sign of dP. So in order to list these as positive quantities, we put the negative sign in front. So again, we could determine what the isothermal compressibility is if the gas would be ideal. So V is equal to nRT over P. So dV dP at fixed T is minus nRT over P squared. So when I stick that into the expression and put in for 1 over V, that is P over nRT, and cancel everything out, I get that the isothermal compressibility of an ideal gas is 1 over the pressure. So at high pressures, what we're saying is that this value is close to 0. You can't squeeze gases that are already at high pressure by very much, is what this is saying. What about at low pressure? Then the gas has a high kappa T value. And of course, what that's saying is when the gas is at a low pressure, any small amount of change in pressure that it experiences will give it a sizable amount of compression onto that particular gas. Again, remind ourselves about something we talked about at the end of our last lecture. That was the Joule-Thomson coefficient. That is defined to be nu is equal to dt dp at constant enthalpy. This was done by experimental design of two of the important contributors, to thermodynamics. Lord Kelvin, who was William Thomson at the time that this was done, and James Joule, who of course is familiar for the definition of what we call the SI unit of energy, is defined in his honor. He did all kinds of interesting work on measuring the temperature change when you do mechanical work in a system. Now, this is defined mu as dt dp at fixed h. It's an isenthalpic process, and it can be made isenthalpic in an adiabatic case, and it measures the gradient of temperature, and it says that when things are expanding, again, going from a low pressure or higher pressure to low pressure. So if you have a gas under pressure, you have a negative temperature gradient. Typically, the Joule-Thomson coefficients are positive. So what that's saying is that you have a negative temperature gradient when you go from high pressure to low pressure. Gases cool upon expansion. And again, I argued this in our last lecture, that maybe you've seen something like that occur on the regulator of a LP liquid propane tank when you cook crawfish or something and the thing starts getting low on gas. You quite frequently see the regulator on it starting to ice up because there's such a dramatic cooling as the liquid expands coming out of the nozzle and into the burner. You can put your hand on that regulator and feel how cold it is getting. Even if there isn't ice on it, try that out sometime when you're hanging out. We can make these experiments isentropic, as we discussed in the last lecture, so you should look into that. And we talked on the previous slide about the isothermal Joule-Thomson coefficient, mu t, being the HTP at fixed t. And if you'll note, the isothermal Joule-Thomson coefficient, which we saw on the previous slides, is similar to the regular Joule-Thomson coefficient, but there's simply some kind of permutation of the variables t, p, and h. Maybe we can examine that further by introducing the permuter that we talked about in our representation of partial derivatives. So let's apply the permuter to the Joule-Thomson coefficient to see how it's related to the isothermal Joule-Thomson coefficient. Okay, so let's begin with the Joule-Thomson coefficient and apply the permuter to it. The permuter you see on the second line on the left, it's dx dy at fixed z is equal to minus dx dz at fixed y times dz dy at fixed x. Now, I talked in the first lecture about where the permuter comes from. Now we're going to see the power and utility of the permuter as applied to thermodynamic variables. And don't be surprised if I don't ask you to do some manipulations of these types. So maybe you should tune in to some examples of doing this and practice doing a few of these things for yourself. So what I'm going to do is define variables x, y, and z. I'm going to take t as x, I'm going to take p as y, and h as z. And then all I'm going to do is do the manipulation. So that means dt dp at fixed h has to equal minus dt dh at fixed p times dh dp at fixed t. So that's how I can express the Joule-Thomson coefficient, and then I'm going to apply the inverter to the term on the left on the right-hand side, the first term on the right-hand side in my second line there. So I'm going to change dt dh at fixed p into dh dp at fixed t, which is the isothermal Joule-Thomson coefficient. So the other term, I recognize dh dp at fixed t, also has a thermodynamic connection. That is the constant pressure heat capacity. So by substituting these things all together, what I find is that the regular Joule-Thomson coefficient is equal to the negative of the isothermal Joule-Thomson coefficient divided by C sub P. Let's see what our newfound relationships between permuters and Maxwell relationships and so forth have to say about the two forms of heat capacity. Remember, we have noted all along that heat is not a state function, it's a path function. So the heat manifests itself in a thermodynamic expression differently whether you work along a constant pressure path or a constant volume path. So we have two different forms of the heat capacity depending on which way we design a system that we are making energetic measurements on. Okay, so let's just look at the difference between C sub P and C sub V using the definition of C sub P is dH dt at fixed P, and using the definition of C sub V is du dt at fixed V. So C sub P minus C sub V, as we see on the first line of equations, is equal to dH dt at fixed P minus du dt at fixed P. Now what I'm going to do for the first term, dH dt at fixed P, is substitute in that H is equal to U plus PV. So I need to take H equals U plus PV and take the derivative of that expression with respect to T at fixed P. So what I have in the middle of the line, it begins by saying C sub P minus C sub V. Then I'm going to put in my dH dt at fixed P term. So I'll substitute H is U plus PV. So I put in the U piece, and I have a PV piece. And notice, because it's constant temperature, the dP dt at fixed T, part of that product rule dies. So Cp minus Cv is du dt at fixed P plus P dV dt at fixed P minus the definition of C sub V, which is du dt at fixed V. So now for the first term on the left in the middle, I'm going to put in du is C sub V dt plus pi t dV. And when I put that in for the term on the left, du dt at fixed P is C sub V plus pi t dV dt at fixed P. So now I'm sticking that in for the term up above where I see du dt at fixed P. Gathering up all the terms that survive from the previous slide, I notice I have a cancellation of CV on both sides of the equation. Then for the dV dt at fixed P, I can substitute something we've already learned that we called the coefficient of expansion alpha. And when I put that in, I get this nice general expression. Cp minus Cv is equal to alpha t, or I'm sorry, pi t plus regular P times V times alpha. So this is a completely general expression again that I have for the difference between heat capacities of any gas, real or ideal. Now, if the gas happens to be ideal, of course, we've seen that pi t is 0. We've also seen that alpha is equal to 1 over t. So I can eliminate the pi t term if this gas is ideal. And again, for alpha, I can put 1 over t. So C sub P minus C sub V for an ideal gas is PV over T. And PV over T is equal to NR. So for the ideal gas, C sub P minus C sub V is equal to NR. This is something we have argued many times over during the course of the semester. Cp is equal to Cv plus NR if the gas is ideal. Now again, we made arguments of that type. This is just another example of proving that using our newfound powers of manipulating partial derivatives. On this slide, we're showing some more manipulations of partial derivatives and tricks we can employ to derive alternative definitions of the heat capacity difference. Again, I saw on the previous slide that the difference between the constant pressure and constant volume heat capacities was the internal pressure plus regular pressure added together times V alpha. And again, if for the ideal gas pi t is 0 and alpha is 1 over T, that becomes that Cp minus Cv was equal to Nr because it was equal to PV over T. So that's what we learned on the previous slide. Now what we're going to do is for my pi t, I'm going to substitute something we learned from the previous slides, that pi t was t times dp dt fixed v minus p. So I substituted that in, and when I do so, I simplify the form down so that Cp minus Cv can be expressed as T times dP dt at fixed V times V alpha. So that's another alternative expression for the difference in heat capacities. I can apply the permuter to dP dt at fixed V. And if I permute dP dt at fixed V, you'll notice I can write it as minus dP dV at fixed T times dV dt at fixed P. Then I can invert the term in the front to make it look like 1 over dV dP at fixed T, which is, and then I note that this permuted form of the expression dP dt at fixed V is simply alpha divided by KT. That has units of P over T, as it should for that expression. So a general expression for Cp minus Cv, which eliminates the internal pressure and writes it in terms of the isothermal compressibility, is that Cp minus Cv can be found from this collection of variables. This is true for a real gas, or an ideal gas for that matter. And for the ideal gas, you should recognize that you can substitute that alpha is equal to 1 over T, so alpha squared is 1 over T squared, and that kappa T is 1 over P. So the right-hand side of that for the ideal gas, again, simplifies down to PV over T, and the right-hand side of that then being PV over T is equal to NR. So this expression simplifies down to the ideal gas expression, just like the one we saw on the previous slide. Here we play more fun games with our partial derivative relationships. Now we're going to manipulate the isothermal Joule-Thomson coefficient into a form involving the expansion coefficient. So I will begin with the fundamental equation for enthalpy, and I'm going to attempt to make it look like the isothermal Joule-Thomson coefficient by dividing by P and imposing constant temperature. So I get the dH dP at fixed T is T ds dP at fixed T plus V. Then I find a Maxwell relationship. As a matter of fact, the third Maxwell relationship, actually, I'm sorry, that's the fourth one, between the pressure and temperature and the entropy. I substitute that in for the expression that I found for my isothermal Joule-Thomson coefficient. It makes it look like the expansion coefficient. So when I substitute that in, I can come to the conclusion that the isothermal Joule-Thomson coefficient is 1 minus alpha T, parentheses, times the volume of the situation. Again, this is an exact equation, true whether the gas is ideal or whether it's real. Now, as a matter of fact, when it is ideal, alpha is equal to 1 over T. So you get 1 minus T over T, which is 1 minus 1, which is 0. The isothermal Joule-Thomson coefficient is 0 for the ideal gas. We can also use our new tools to derive a general expression for the adiabatic expansion of a gas, whether it is real or ideal. Now, what we had done now several tests ago even, was for the ideal gas, we were able to come to the conclusion for the reversible adiabatic expansion of that real gas that TF over TI was equal to VI over VF raised to the R over CV power. So we did all that before, a long time ago. You can look up how we came about doing that before. Now let's do it completely generally based on our new tricks that we've learned about manipulating partial derivatives. I want an experiment, and I can just think of the design of the experiment: adiabatic expansion of a gas. That means I'm interested in dV dt at fixed S. Adiabatic is the fixed S. Expansion with temperature is the dV over dt, stuff that I'm looking at. So I need to find how to do dV dt at fixed S. So what I'm going to do is permute the variables v, t, and s and see what it does for me. I just use my definition of the permuter, stick in x, y, and z as v, t, and s, and I learn that dV dt at fixed s is minus dV ds at fixed t times ds dt at fixed v. So then I substitute into that ds is dq over t, which for constant volume is ncv slash t divided by t over dt, or times dt. And so I get that the left-hand side of that equation, dv dt at fixed s, is equal to minus dV ds at fixed t times my ncv over t for the term on the right. So now what I'm going to do is invert the term on the right. As you can see at the bottom, I simply used my inverter to flip the term on the right over. Then what I'm going to do on the next slide is find a Maxwell relationship for that term. Okay, so what I'm going to do, I'm just bringing this equation over from the previous slide. I'm going to go to my Helmholtz energy and the Maxwell relationship for that Helmholtz energy. It says that ds dV at fixed t is really written in terms of the mechanical variables as dp dt at fixed v. And so then I have my general expression for any gas for the adiabatic expansion of that gas. It has to be equal to minus CV over RT over V if it's ideal. So that's what it would be if it's ideal. Then I can just collect the variables of T on one side and V on the other. And if I were to integrate both sides of that equation, I get the expression that I got previously for an ideal gas. But what I'm going to point out to you is the expression on the second line is completely general. It's not till I go to the third line that I'm making the gas ideal. The second line is a completely general adiabatic expansion of any gas, whether it's real or it's ideal. It can be expressed, as you see, in terms of the values that are written in the form on the second line.